Previously, we introduced Newton's laws of motion and applied them to situations involving linear motion. Now we are going to apply Newton's laws to objects traveling in circular paths. In the preceding chapters, we have modeled a particle which undergoes uniform circular motion. And we know that the acceleration experienced by the particle is equal to centripetal acceleration. Here, v is the uniform velocity of the particle and r is the radius of the path. This acceleration is called centripetal acceleration because it's directed toward the center of the circle. And for uniform circular motion, centripetal acceleration is always perpendicular to the velocity. Now let's apply Newton's second law of motion to our circular motion. The force causing the centripetal acceleration acts toward the center of the circular path. This is the force that keeps the object in its circular trajectory. If this force vanishes, the object no longer goes in a circular path. Imagine a ball tied to a rope being whirled. The tension on the rope holds the ball in its circular path. And if the rope breaks, that tension that holds the ball in its circular trajectory will vanish. And since there is no force holding the ball in its circular path, ball will leave its circular motion. Now let us see if we can analyze this problem. In the problem, a small ball of mass m is suspended from a string of length L. The ball revolves with a constant speed in a horizontal circle of radius r. During its rotation, the string sweeps out the surface of a cone. This is why this system is called as conical pendulum. And let's try to find an expression for the velocity of the ball. When we investigate the problem, we see that there is no motion in the vertical direction. And perpendicular to the velocity vector, there is only a centripetal acceleration. So the ball is experiencing centripetal acceleration. What about the direction parallel to the velocity vector? There are no force components parallel to velocity vector. Okay then, but before starting to mathematical analysis, let's try to draw the free body diagram of the ball. We all know that the drawing of the free body diagram is one of the key elements of force analysis. We isolated the ball from the system and projected the tension T to its vertical components. And the coordinate axes are defined as shown in the figure. Now let's try to write down our force balance equations. In vertical axis, I'd like to define the positive y as my positive direction. So I should put a plus sign in front of every forces that are looking upward. So total sum of the forces in the vertical direction is equal to t times cosine theta minus m times g. Since there's no motion in the vertical axis, this equation should be equal to 0. Let's name this equation as number 1. And let me name this equation as number 2, and I want to tidy up this equation a little bit. Now I'm going to divide this equation into this equation. And if we solve this expression for v, the velocity of the ball, but I'd like to add one more thing. I want to express this radius r in terms of the length of the string. It is more practical than using the radius. This is our final expression for the velocity v. Okay, now let's see what happens if the velocity of the object is not constant. If the velocity of the particle is varying, there is also a tangential component of the acceleration. Therefore, the total acceleration can be expressed by the sum of the radial and the tangential acceleration components. Similarly, the net force acting on the particle also has two components in both radial and tangential directions. Here, the radial force is responsible from the centripetal acceleration, and Ft is responsible from the tangential acceleration. Now let's try to solve a non-uniform circular motion example. In the problem, a small sphere of mass m is attached to a cord. Here the green line represents the cord. And the sphere is rotating on a vertical plane. Therefore, at every instant, the gravitational acceleration is present. At the topmost position, the tension on the cord and the weight of the sphere is directed downward. When the sphere is at the lowest position, the tension of the cord is looking upward. And the top and the bottom positions are denoted with BOT and TOP. Let me erase those lines to make it less confusing. And when the sphere is at the bottom, its velocity directed to the right. And when the sphere is at topmost position, its velocity directed to the left. When the angle between the vertical and the cord is equal to theta, the tension on the cord will be directed to the origin of the circle, similar to the other cases. The weight of the sphere the weight of the sphere will be directed to downward. And for the weight of the sphere, it will be much easier to analyze if we project the weight onto tangential and the radial axis. Here, this vector represents the radial component of the weight of the sphere, and this vector is representing the tangential component of the weight of the sphere. Using these trigonometric expressions generalizes the whole model. For example, when the sphere is at the bottom position, cosine theta will be equal to 1 and sine theta will be equal to 0, which give us m times g only. Similarly, when the ball reaches to this position, the radial component of the weight will be 0, because cosine theta will be equal to 0. So with the help of these trigonometric expressions, let's write our force balance equations. In the tangential direction, there is only one force component. And in the radial axis, we have two force terms. First one is the tension on the cord, and second one is caused by the weight of the sphere. Okay, let's name these equations as equation number 1 and equation number 2. Let's evaluate the tension on the cord for the bottom and the top positions. And for the bottom position, we can obtain the tension on the cord as this. Okay, in this video we have learned how do we analyze force problems with uniform and non-uniform circular motion.